when we are both in a conference, there is one thing that we fear, Bruno and myself, is to be presented by the other. So my biggest fear is that Bruno makes the introduction for me. And I believe that Bruno's bigger fear is when I do the introduction for him. So I will try to do it. Well, let's say, okay, so no need to introduce Bruno as a person and his career, etc. Just what I want to say that Bruno has devoted his life to understanding the volatility surface, plus a few other things, but that was a big, big part of his life. And so he's going to talk about that, if I understand well. Anything like this, or is still related to the what do you call that? You know, your functionality calculus and things like this, or is it both? Or?
Yeah, actually, I will cover both local volatility model and a little bit of functionality calculus, but it's both serving to introduce and to illustrate the topic.
So Bruno, floor is yours.
Thank you. So let me try to find the right window here. Do you see it here?
Yes.
It's okay, wonderful. But first of all, so actually they give me 1 hour. So
yeah, you're in full screen, Bruno. You're not. You're in full screen.
So what do you see here? Oh, sorry.
No, we see your screen, but just a matter of size. So I was wondering whether you're in full screen or not yet, because I'm.
Something happened.
Just make sure you're in full screen.
No, it was okay. It was okay.
Okay, very good.
So you see mostly the front slide, I guess, yeah.
Exactly.
Okay, so I have quite a lot of time, so I think it's quite appropriate to start with Marco, actually, knowing that it is so the honor, the birthday boy, I would say, this year. So Marco, it's it has been a pleasure to spend all these years through Rio and many other conferences or socially. So just going back very briefly in time, I think we met initially through Raphael, actually, when you were both organizing this Courant Institute Math Finance Seminar. I think it was at 5:30 p.m. on the Thursdays. And so it was really a very nice and instructive weekly meeting that everybody was looking forward to. After it was, in some sense, the ancestor of what I've done after, which is this BBQ, the Bloomberg Quant Seminar, that is happening every month. So we met. It was mid-90s, and after we've been socializing in many different locations. So just to mention a few, obviously we had Rio, Buzios, and this, but also the Côte d'Azur and where I used to live for some time, close to Nice, and different funky places. And an interesting one 2 years ago, actually, was in Jerusalem as well. So it's many great rememberings of interesting discussions and great fun altogether. So Marco is having a very rich scientific life. So after this pure math, he has been contributing a lot in finance. So, and this has been sort of recognized by different awards, like Risk Magazine Quant of the Year award. And for the different contributions. So obviously, this is something which sticks out. It's an uncertain volatility model in the 90s. Actually, you developed it with your student Antonio Parras, whom I happened to hire after at Paribas, and to give him his first job. So we went back to this model, revisiting. So it was quite interesting to see the richness of it. You've done quite a few other things, so like the weighted Monte Carlo method. You have popularized entropy methods in finance, and plus more recent work like what has been mentioned, for instance, today, which were, for instance, the analysis of the market with different forms of a PCA, so either on the stocks or on the volatility, or the work in volatility. And it has been, in short, it has been a pleasure scientifically and in terms of a friendship, yet to have known you for all these years, and actually to have shared the creation of this Rio conference, the Research in Options, back in 2006. So it was the two of us, plus indeed George, who was doing actually the real work. Thank you. So thank you, compadres, for having shared all these moments. So now I'm going to move to my presentation. So actually, it's to revisit quite interesting topic and useful, very useful topic, because it's the forward equations is a way to speed up tremendously the joint computation of many different options under some circumstances, and I will try to clarify which ones they are. And so it's what has made it possible to have, for instance, my local volatility model that I developed back in '93 to make it useful, and actually this helped the local volatility model to become the second most used models in equity derivatives after, indeed, the Black-Scholes one. So in this presentation, I will try to explain, actually to show a way to obtain forward equations, which is quite linked to how a trader maybe would interpret, would understand it. And interestingly, we'll see that it's a way to obtain the Black-Scholes equation in a kind of simpler way than the way they did it themselves. And it's not using explicitly arbitrage or a hedging argument. It's not operating under transformed measure, so no change of measure, no dynamic replication. So essentially, it's mostly Ito's lemma and basic accounting. The benefit of it is that also it helps us to understand what you can obtain and not obtain. And actually, the fact that we have this forward equation, for instance, in the local model for vanilla options, it's a bit of a miracle. Actually, it's a combination of two miracles, or let's say mysteries or happy coincidences. So let's go into it. So first, what do we mean by backward and forward equations? So it depends on what you consider to be a variable and a parameter. So you want to price options. So the option is defined by its payoff, which depends on some parameters. Typically, a vanilla European call option would be just defined by the strike and the maturity. And the price will be the price of this option within some model. For instance, in Black-Scholes, so it will depend on the spot price, interest rate, and mostly volatility. So in a Markov model, the European call price will depend. So if we assume that we freeze, for instance, the interest rates, and actually for many examples, I will assume that there is no carry term, so it means no interest rates, no dividends, no repo, to really concentrate on the concept and not on the notation. So the call price depends on this market variables, so which are, for instance, the spot price and the current time and the parameters of the option. which is the strike and the maturity. For instance, in Black-Scholes, I keep this variables because the interest rates and the volatility are fixed, part of the model. They are model parameters and not state variables. So the backward equation, as you know, consists in looking at one given option, fixing the strikes and the maturity, for instance, and the backward PDE, which expresses the trade-off between the gamma and the theta, what you gain through the convexity and what you lose through the time value that decreases through time. So it takes as variable S and T, so K and capital T, strike and maturity are fixed, and the current spot price and the time are the variables of the PDE. So the PDE starts from the end, from the payoff, and goes backward in time and computes the price of the option for at all intermediate time and in different spot values. The forward equation will invert this view, so it's a kind of dual view of it, where actually you freeze the spot price and the time, typically the current market conditions, but the price that you will compute will be the price of all options of different strikes and maturities, and in progressing in a forward fashion in time, actually in maturity in that case. Sorry. Sorry, it was frozen, and let me go back here. So let's go first to the volatility model. So very briefly, so it started when I was working for Société Générale in 91, 92, and mostly for the pricing of barrier options. So barrier option for here, it's an example, for instance, of an up and out call. So for instance, the strike is 100 and the out level is 120. So the option disappears when it hits the barrier, which is in the money. So when the value would have had quite a lot of value otherwise. So it depends. So intuitively, it's not very easy to know how to handle this if the only thing you know is the Black-Scholes model, is a single volatility, because you have two parameters. You have the strike and the barrier, and it's not clear how to combine those to obtain the price of the up and out call. So it's reasonably easy. Actually, it's not easy, but it was already done by Merton in his paper of 1973, The Theory of Rational Option Pricing, to compute the value of such an option within the Black-Scholes model. So it's tempting to think that we can just we just need to adjust the volatility parameter to obtain to be able to take into account those the two implied volatilities corresponding to the strike and the maturity. The problem is that in an option like this, an up and out call option, actually around the strike you have a convexity, so you're happy to have volatility there, but around the barrier, so you have a big concavity actually, and increasing the volatility makes it more likely to lose the option. So in other words, the volatility at the strike is a good volatility, and the one at the barrier is a bad one. And when you combine them, actually, you have to sort of extrapolate and those two volatilities. It's not to use one in between. And actually, the problem is that it gives you, when you compute the option in a proper model that takes the skew into account, you get a price of the option which is actually quite high in a typical equity market where the skew is negative. So in my example with a strike of 100 and a barrier of 120, you have this high good volatility and low bad volatility combined effect here, as you see in this graph, would be to have a price of something like 1.3 on this, the corresponding to the flat orange line. Now, when you price with Black-Scholes, with different volatilities, actually, if you start from zero volatility, so if you start a bit out of the money, so the price is zero and then increases. But if you increase it, if you increase the volatility more, it becomes very likely to lose the option. And actually, the price with the skew is higher than the price in any of those Black-Scholes model. So here I put nail is a bear option pricing, and the hammer is a LVM. In the classical tradition of mathematicians, to call a hammer, let's say, a method or a principle, and a nail, it's a problem to which you apply the hammer. What is common in mathematics is to first come up with the hammer and after to look for a nail to justify what you did. But in finance, we have plenty of nails, and actually the issue was to create the hammer. So just a very simple view of the local vol model, again, with no interest rate to make it simpler. Black-Scholes, you have a constant volatility. In the Merton model, actually, of the 73, you already had time-dependent volatility, because as you know, the only thing that matters is the cumulative variance, so the integral of sigma square. And so the simplest, so in the Merton model, allows you to fit the term structure of volatility, or the variance swaps, if you want. And the question was to know how to have an extension, the simplest possible extension, compatible with the whole surface. So natural candidate was sigma of S and T, because it's a one-dimensional Markov diffusion. And so this is the local volatility. Sorry. And sorry. Yeah. So if you manage to do this, then you manage to establish a link between the European prices of the prices of vanilla options, because they will be equivalent to the local volatilities that you can use to price a more complex one, like a path-dependent options. So this allows you to establish a link between European option prices and the exotic option prices, and actually to construct a sound risk management to know how to optimally protect, hedge the exotic options with the vanillas. So this local volatility model here. So the question was, is it possible to find sigma of S&T that fits the whole market? And is there only, if it's possible, do we have uniqueness? And so what is very nice, it's actually that yes, if you start from smooth arbitrage-free prices, it is possible to do it, and it's only one way. And on top of it, it is explicit, and it will be given by this forward equation. So if you think of a space, of the set of the different possible models, and if we imply some constraints, so here the red circle, it's a one-dimensional Markov diffusions, and so the green one, it would be risk-neutral processes, typically without carry terms, it means martingale. And if you want it to be compatible with the market smile, so with the, it means to the whole implied volatility surface. So the nice thing is that you have one solution and only one. All the other pairwise intersections are non-void, and actually a lot of effort is devoted to the intersection of green and yellow to possibly calibrate models to other things like the dynamics actually of at the money vol, or different the price of forward start options or other barrier options. So the way I obtained that initially, so it was by integrating twice the forward Kolmogorov equation, called also the Fokker-Planck equation. So let's look at the link and the similarities and differences between the backward equation and the forward equation. So the backward equation is the Black-Scholes PDE. So that tells you that the time value, the change of the time value. So it's a negative term. It's a time erosion. So it's linked to the half of the variance time. So here it's Black-Scholes expressed already in the case of sigma of S and T. And here you have the gamma term, the convexity, because convexity is a way to capture volatility. So you have this trade-off between the what's called the theta on the left-hand side and the gamma on the right-hand side. So forward equation will be exactly of the same shape, except inverted roles for the variables and the parameters. And so it's with a plus sign here. And so I would like to make sure that I'm able to share my point here, which is that a nice way to interpret this equation here, it is to interpret the left-hand side as the cost of extending the maturity of an option, and the right-hand side explains, links it actually to different quantities. And actually, this second derivative here with respect to the strike, due to the result of Breeden-Litzenberger, it's a risk-neutral density. Yeah, but this interpretation of a forward equation as the cost of extending the maturity is really very, very fruitful. So let's look at. I should have decomposed this probably in two slides, but here it's a very simple way to obtain it. So again, without invoking anything like dynamic hedging or change of measure or Tanaka formula, these kind of things. So you assume you have a dynamic. So here I'm not starting from the risk neutral one, but the real world dynamics with some drift, even if there is no carry. You may have a drift. The risk neutral drift would be 0, but we do not assume it's the case here. So now we look at a function just of S, so of a single variable. There is no time in it. When we apply Ito's formula to f of S, then you obtain, so there is no time derivative. It's just first and second order derivative in with respect to the variable as the spot price. And so we have this term here, and the first order term and the second order term. The first order term is replicated directly by using, as you know, the quantity of stock, which is f prime of S. So actually, you don't even need to replicate this. What matters is that actually the cost of the first term is 0. From 0, you can generate this by again just having a position in stock equal to f prime of S. The second term here, so the second order derivative gives you a deterministic term given by this. So how do we interpret this? We interpret it by saying that by realizing that so the cost of extending the maturity of an option that gives you a payoff f, which would be the same at all maturities. So it is just the second term, because the first is costless, it's self-financing. So if you have, just to give you an example, if you have, for instance, an option, a European type option that gives you a pair of f of S at a maturity, let's say 1 year, and you want to extend the maturity by, let's say, 1 day. So once you arrive at in 1 year, it will have an extra cost, which is the Ito cost here, which is half the variance times S squared times this second derivative. So that's a general result. This would be the cost in a model like this to extend the maturity. And now you can forget about Ito's formula and the local time or whatever. So you can just apply this result here in the special case of F being the hockey stick payoff, for instance, of a European call option. So in this case, the F double prime become a Dirac mass here. So actually, the cost of extending, it's a Dirac mass with a mass being sigma squared, k squared over 2. And now, so we can interpret this cost of extending the maturity of the option in another way as well, which is, what is, if I know the price of those options for all strikes and maturities, so I can express the cost of extending the option just as the first derivative with respect to the time of this this price function. So I have two ways to express this cost of extending the maturity. One is to see it from now and to say, okay, you have it will be the difference between a 1 year, 1 day call option and a 1 year option divided by 1 day and going to the limit. The second way to interpret it is to look at how much it would cost you in 1 year to extend, to replicate, to reproduce the payoff. Okay, so this logic is very simple. Sorry, what I've not said is that the second derivative with respect to the strikes, so from Breeden Litzenberger, can be interpreted, if you want, as a very tight butterfly portfolio that converts to this Dirac payoff. So it's we have those two miracles now that I wanted to mention. It is, so the first one is that usually we have, if I go back here, and if I look at this this equation, if you see, I don't know. Sorry, the one where you see no Ito anymore now. So actually, what is the value today of the present value, if you want, the PV of this that will be paid in 1 year? So in general, so as S can take any possible value, it will have the shape of an integral. So that's a first complication. And the second thing, it is that we have to be able to price a Dirac function. If you write the payoff as an integral of the value times the Dirac function. So we have two issues. One is that we have the integral. The second one is what is the price today of a Dirac. And actually, so this is a very nice thing. It is that when you take a hockey stick pair of the second derivative becomes a Dirac mass and the integral boils down to a single point. And the second thing is that the price of a Dirac can be expressed in terms of call options because it's a tight butterfly which can be seen as a finite difference of the second order that converges to the second second derivative. So it's quite fortunate that actually those two facts, those two miracles can be combined and to eventually having this this equation here in the bottom. And actually, when you have, I will show what happens when you have carry terms, and it will depend on the structural shape of those of the interest rate or dividend, for instance. But another way to put it is actually it's quite fortunate that when you integrate twice a Dirac function, you get a hockey stick payoff, and that it happens that it's where the market is trading. Okay, so another beauty of this forward equation, so it's that it does work with simple carry terms. As I mentioned, it will depend on the structure of them. So if you have interest rates, so basically you have to consider three cases once you arrive at the maturity. Either you're out of the money and everything will be zero, or you close to the strike and you have this volatility term that we just considered, or you're in the money where you have the carry terms, carry cost to extend the payoff. And the very nice thing is that in the case of, for instance, interest rates, if it's a constant interest rate, actually it leads to a constant value when you're in the money, and it corresponds to a digital payoff, which is actually a derivative, first order derivative with respect to the strike of the call option. So all those things can still be expressed in terms of the derivatives of the call option price. When you have dividend yield or interest rate, foreign interest rate for currency options, so actually the cost of extending the maturity will be linked to a call option itself. So eventually all this remains within this family of the call prices and their derivatives through this equation here. So if the interest rates depend, for instance, on the spot price in general, so it would give you a whole payoff to value that will be explainable, expressible in terms of the call options, but in the form of an integral. So you would lose this PDE, it would become a PIDE actually. So again, it's quite fortunate that with the simple assumptions, everything works. But so this should convince you that it's not a very generic property in general. Here, it's we've been quite lucky. Okay, so here, as I said, so it was so it's to illustrate actually the power of the approach is that it gives you a celebrated formula result, the Black-Scholes PDE without the usual different ingredients that are needed, either hedging argument for the PD or change of measure for martingale methods. So you would say, oh yeah, but actually you get a forward PD, not a backward PD. But the important thing is that actually it's two different ways to compute the same value. If eventually you're interested in the price today of a certain option with certain strike and maturity, so you can do it either in a backward way, starting from the payoff of that option and working back in time to get the price today, or you can propagate the price of options, the today price of options through the forward PD. So it's two different ways to get the same thing, but I would argue that the forward one is simpler. So other powers of it, instead of the educational virtue of it, it is that the forward equation, so I mentioned it already, allows you to compute the prices of all the options from the start. Instead of, okay, if you want to calibrate a model, for instance, and you want to look at what your assumption of okay, no, sorry, let me rather say it this way. If you make an assumption on the local volatilities and you want to see what are the implied volatility that you get, so the usual way would be for each option, each strike and maturity, to run a backward PD, so a double family of them, which is heavy computationally. Here, you just do it in one single sweep. And so this is help you for fast calibration of the model. The second approach is the implied volatility. If you start from an implied volatility surface from the market, typically you have from the discrete values of the market, you interpolate smoothly, and then you can compute the local volatilities through this formula. So when you have the forward equation, so you can use it either to propagate, to compute all the prices if you know the local volatilities, or if you know the prices, you get the local volatilities. So yeah, as you know, so it allows you to go from, for instance, here S&P implied volatility, S&P 500. No, I'm sorry. Here it was JP Morgan. Yeah, and you get local volatilities that look the same. Essentially, it exacerbates the shape of the initial one. So, summary of the local vol model. Personally, I would say that even if it's extremely, very much used everywhere, it's not a good model in the sense that it's not a good predictor of the behavior of volatility in the future. But what is important is really the concept of the local volatility as a forward quantity, an instantaneous forward quantity that can be locked in. So actually, more precisely, it's on the variance. It means that if you have a frictionless market and you compute your local vols, and someone disagrees with those levels and is ready to trade with you, you can arbitrage. When you have a stochastic volatility, then this is something that that I showed in my paper, UTV, Unified Theory of Volatility in '96. It is that a stochastic volatility model will be calibrated to the market if and only if it satisfies the local variance given by this ratio of the local, of the derivative of the call prices with respect to the strike and maturity. Another interesting result is that if you have a model where the implied volatility is a deterministic function of the spot price and the time, and without the jumps, then it has to be actually what is given by the local volatility model. This is important because many risk systems make some assumptions, like, or if the stock price moves down by 5%, then volatility should be here. And most of the assumptions actually are creating arbitrage. So this was a recap of basically forward equations for vanilla options. So a natural question is, what would it mean? Can I give a meaning to a generic payoff f of s for the strike, so the max of s minus k and 0. So it's clearly parameterized by one quantity, which is a strike. But if I have f, I mean, I just had one kink, one angular point. But if I have a generic payoff f, possibly smooth, what does it mean? So a natural way to extend f into something that depends on a parameter, just to do the same thing that we had here. Basically, it's to consider a shift. Here I keep the same, I use a bit of notation to keep f also as a function of those two variables, where k is a shift parameter. And so what we'll see, I think a bit after, because it works in the case of several dimensions as well. In the case of the Bachelier model, so which is a constant absolute volatilities, then actually we can get a forward PDE for arbitrary payoff defined as a function of the strike, the shift parameter. Yeah, sorry, here it is. And Here it's written in one dimension, but it will be the same for n-dimensional case. So if you have a pair of f, a certain function f, so we define k in the shift parameter, and a of k and t would be the price of this option under with the shift for that maturity capital T. So the price of it would be, so it would be a multi-dimensional integral in general. In the one-dimensional case, just so it's you integrate the value of the option, the payoff by the risk-neutral density for that maturity, and here we are going to use just the translation invariance of within the Bachelier model, actually. So, no, sorry, we just perform a change of variable here, so which allows you to keep just f here, and we apply the shift now to the density. So now when we differentiate the price with respect to time, and after we do it with respect to strike, we can use the fact that phi satisfies the forward Kolmogorov and the Fokker-Planck equation. So if we differentiate, we do it under the integral, and here we apply the Kolmogorov relation. And so here, as sigma square is constant, we take it away there. And you can take the differentiation outside of the integral, and to reconstitute here the integral with being the price a, the a of kt. So this establishes that actually, sorry, there is a missing time derivative here, but we have the same forward equation if we have a constant volatility, but for generic payoff, and to which we apply a shift parameter, and it works in the n-dimensional case as well. So other types of extension. So indeed, it's with stochastic volatility and the stochastic rates. So basically, we'll see we can extend the result to two different things, either different dynamics or different payoffs. For the dynamics, so with stochastic volatility, so and rates, it's still the logic that I explained in the case of a Hawkistic payoff. You will have to distinguish between those three scenarios at maturity, whether you are out of the money, where everything is zero, where you're at the money, and then you have this variance term, and the carry terms if you're in the money. You have many people have been looking at jumps as well. Yeah, the different people like Anderson and Andreasson, I think Rama and other people have looked at it. You have path-dependent models with some partial results, and the multi-dimensional one. So for the multi-dimensional one, it's quite interesting because there are some things that work in 2 dimensions and not in n dimension. Very often, if you can do it from 1D to 2D, it works just to ND. It's kind of purely notational. It's not always the case. For instance, if you have a local volatility model on X, a local volatility model on Y, and if you know the price of all the options on X and Y, you can combine them to get a 2-dimensional Dirac, and you can actually create a model where the local correlation will depend on X, Y, and T, but it does not work for further dimensions. Okay. So when we have path-dependent options, so the question is to know what you can do or not do. So you have to distinguish the payoff itself. It can be it's often defined by very few parameters. For instance, for a barrier option, you just add up a single parameter, and so if there is a really forward equation, then it will be quite simple because it only depends on these few parameters with respect to which we differentiate the price. But if it is if you have a dependency which is deep, let me give you an example. For instance, if you have a payoff, let's say you have a 1-year option that gives you at maturity the maximum of the rolling 1 month average, for instance, then it is not reducible to a small number of variable, and actually we have the backward equation. So I will cover this. Yeah, you have it just below here from the functional Ito calculus I developed in 2009. So it has the same shape as the Black-Scholes PDE, but the derivatives have to be understood in the functional sense. And actually, it's at each, we are in a path space, not in a low-dimensional space. And so basically, it's much more involved in terms of the numerical method, for instance. By the way, Yuri Saporito, maybe you're listening, but he has a very interesting paper on making use of the neural nets to address this situation. But yeah, the point is that here you may have, okay, how can I say that? The option may be defined by a few parameters, and if you have a forward equation, it may be simple, but the backward equation is, if it's depending on the whole path, in general, it's not simple. So, sorry. Yeah, here a very brief primer on the functional Ito calculus. So it's due to the fact that, yeah, in math in general, and especially in finance, people love to work in Markov setting because it's easier to understand and to compute. But actually, there are many reasons in finance to not be Markov. It can be easier because the product, the option, has a path-dependent payoff, like all those exotics with a look-back Asian, forward start, barrier, or the dynamics can be path-dependent. Like, for instance, path-dependent volatility or path-dependent dividends. Dividends tend to be highly path-dependent, by the way. But so we can. The good news is that it's possible to extend the functional Ito calculus to a functional Ito calculus, essentially retaining the same results and the shape of the formula, just with extending the notion of derivatives to of a variable to a path, actually. Yeah, I don't really have too much time to go there. If you just look at the last thing here, you have a path so far in white, and we consider, when we differentiate, basically we look at the scenarios for the next moment, if you want, in the finite difference logic. So without needing to construct the path until a final maturity, and without changing anything from the past, because it's already there, you cannot change it. So you have, if you have a functional, so it means something that attributes to any path so far a real value, you can you can look at the impact of a vertical or horizontal bump, so price bump or space bump if you want, or freezing the current value over some time, and to look at how it's affecting the value of the functional. So you define the spatial derivative here, delta x, as the value of the functional after this bump in the current variable to minus the oldest value, and you normalize by the bump. We do the same thing for time. So just a simple thing here. If I look at simple functionals, so it will be those ones here. And if I look at the price bump and the time freezing here, not time freezing, but freezing the value and advancing in time. So you can compute the different functional derivatives here. An interesting case, for instance, is the running integral, the integral so far. Yeah, it's from 0 to small t. So if you bump the value today, you don't change the value of the integral, so the derivative is 0. And if you freeze the current value and advance in time, so the integral will increase by the current value times delta t. So after normalization, you get a functional derivative of xt. But now you see that if you differentiate, if you look at the cross derivative, if you differentiate first with respect to the price, so you get 0, and then with respect to time values, obviously still get 0. But if you had done the other way around, if you differentiate first with respect to time, you get xt, and then to x, you get 1. So you have a Lie bracket between those two derivatives, and it's one of the characterizations of path dependency. So we get all the classical results here, functional versions of Ito formula, the Feynman-Cat, of Clark-Ocon formula, actually, for the martingale representation theorem, and the Black-Scholes PDE. We can apply it to get to refine the Crankov optional decomposition for super application, and yeah, it can be used to characterize which claims are attainable, for instance, from a static position in options and with dynamic trading of the stock price. And it can be applied also to decompose the volatility risk. So just briefly, because the graphs are nice here, for the an Asian option, so actually you can find the coefficient of the portfolio of European options that mimics best this, that has the same volatility risk signature, and obtained by this conditional expectations of the functional gamma. So you can do it for different options to have a fine description of the volatility risk landscape. So now let's look at in the remaining minutes to the application to other types of options. So can we have a forward equation for following options? American type options. In general, not, but actually if you have constant parameters due to time, to homogeneity, like the only thing that matters, it's the residual maturity, it's not a precise time and precise maturity. Yes, you have a forward equation for the American option in the classical Black-Scholes model, but not with local volatilities. For barrier options, so again, it has been investigated by different people. Olivier Pironneau, for instance, has worked in different extensions, or Peter Carr. Yeah, wait, Peter Carr actually has done the work also for these American options. And so the answer is yes, you can do the same thing, and actually it's quite simple. So basically the way it works, for a fixed level of barrier, you have a similar forward PDE with just different boundary conditions to express this disappearance at the barrier level. And you can see how it works still with the same logic of trying to understand what is the cost of extending the maturity of the option. So if you extend from, let's say, 1 year to 1 year plus 1 day, you see that you will have a cost only if you arrive at maturity. You have the classical Dirac stuff, and if you have not hit the barrier before. So basically, it will depend on the risk-neutral absorbed density there, which is obtained actually by still a butterfly trade of barrier options. For Asian options, unfortunately, no, you do not have a forward equation, because you would need to have the joint law of the current spot price and the average so far. And actually, you cannot combine Asian options to obtain this information. Look-back options, yeah, it's pretty much the same thing. You would need a joint law for the spot price and the minimum. But actually, if you have barrier options, actually the nice thing is that you can combine different barrier options to replicate things that are linked to the maximum or the minimum. But a look-back forward equation for look-backs from the look-back prices don't work. So yeah, sorry, just before finishing, yeah, for the multi-dimensional case, actually there have been different works, and yeah, I would like to mention also Georges Zuberi has been working also on the, for instance, on the basket case. So it's a kind of a rich and interesting field, and my conclusion is that yeah, it's kind of elegant, interesting, but mostly it's very useful in practical terms to tremendously speed up the computations. So one thing which is very important to understand what can be done or not, instead of just abstract double integration by parts, for instance, it is to have really more of an accounting view or trading view, trader's view of the cost of extending the maturities. And so it's quite enlightening, and it helps you, for instance, you know, checking the sign of what you get. It's easy to get it wrong otherwise. And so, yeah, in favorable cases, this cost of extending the maturity can be seen, can lead really to a forward PD as opposed to a forward PID, which is losing most of the benefit of the approach. Another interesting thing is that, again, it gives you a simpler proof of Black-Scholes in the sense that it's using less principles actually than the original one or variations of them. And another interesting thing is that in the case of Bachelier dynamics, so when you look at an arbitrary payoff and the shift, and you differentiate with respect to the shift parameter, you do get a forward PD even in the case of multi-dimension. So thank you for your attention. So maybe we still have time for some questions.
Bruno, thank you for your very good presentation, and which is both historical and some new research that you have. I'm trying to see if we have questions on the YouTube now. So please, those who have questions, please write them on the YouTube channel. I have one question for you. If you can
I have a question from Raphael, and it's worth
unless someone has
introduction from Raphael.
does someone among the speakers has question? Okay, so let me ask you a question, Bruno. You were working on some paradoxes, you know, on that question about the fact that in certain cases it was very difficult to find actual arbitrage strategies, even though some parameters could not be made precise formally. So can you give such examples and and whether the use of the forward equation can potentially help? But those cases where I remember you told me several cases like that, where you have it's not obvious to create an actual arbitrage strategy, even though that the price has to be in between some bounds.
Oh yeah, okay, yeah. The link to this super replication stuff.
In certain cases, it was very difficult to find actual arbitrage strategies.
I have two Raphaels now.
yeah, exactly. That is two of mine. Yeah. Very bizarre.
That's okay. Yeah, it's a very interesting question. That sometimes you have a mathematical result, that proves that it's impossible. Okay, I give you, for instance, an example: call on realized variance. So there is a result. It's a consequence of the score embedding problem. So basically, it shows that if you have the price of all European options, so it's constraining the price of options on realized variance or on quadratic variation, if you prefer in stochastic terms. And actually, so it's the lower bound is given by actually what's called the root solution to the score embedding problem, which is a very natural way to, score embedding problem is how to stop a Brown motion in such a way the stop density is equal to a target density, which in the market means it would be the risk neutral density for a given maturity, and the stopping time would be actually a quadratic variation. So it's obtained when you stop your Brown motion by an obstacle in 2 dimensions. I mean, the time and the Brownian. And the problem is it's a mathematical result, but how can you convert it into an arbitrage strategy? Which means that if this relationship is violated by the market, how do you operationally build your strategy to capture this difference? Typically for the call on realized variance, if it trades at a lower value than the lower bound, so how can you do it? And actually, it is very, very complicated. It's only a few years ago, a paper by Cox and other people, maybe Nisa Touzi and Obloch, I've gone through the details of it, had an approximative solution before. So that's it's a very interesting problem in finance. Whether it relates to forward equation, I'm not so sure directly, but it's it's a beautiful. Globally, it's a beautiful application of geometry because, as usual, many of these problems boil down to applications of the Anbana theorem. Let's say, there's a collection of different situations where it's far from obvious to convert a mathematical result into a trading strategy when the market violates this mathematical things. So I had worked, I had quite an interesting presentation more than 20 years ago of how to turn mathematical results into arbitrage strategies, and you can do, for instance, the Cauchy-Schwarz inequality or this kind of things. It's quite simple. But you can go actually to stochastic calculus results like Dupes inequality to look at how to use it if it's violated. So it means when you have a martingale equality or inequality, so it corresponds, it can be seen to you have two terms, and each one can be seen as the payoff of some path-dependent option, because it's typically the expectation will be the risk neutral price. And so
thank you, Bruno. We're a bit out of time, so thank you. I mean, that's let
okay.
me. We have,
I did it for two, but you can do it for
exactly. We have two questions, so let me read them, and either you choose to answer one or you choose to answer very shortly to both of them. First question from Luis Octavio Rocho about the gamma theta trade-off for path dependence options. Ito formula calculus could give us a little more details on this matter. This question. The second from Christian Alcaraz. What is the main advantage of obtaining local volatility analytically compared to estimating volatility using Garch or stochastic volatility models?
Okay, so I try briefly the two. The first one. So actually, the PDE of Black-Scholes really expresses in a nutshell what I said, the gamma theta trade-off, and that's really a reality for the traders. And for a long time, for me, it was obvious that the same thing would apply to path-dependent options, and I've been using the result for different risk analysis, and until I realized that it had not been done really to express to prove it. And actually, it's kind of amazing because there's a vast literature about path-dependent options, but basically they were unable to express, to define the notion of Greeks, of sensitivities properly. So I started from a little nail, and I realized that I needed a pretty big hammer to do this. But essentially, so it's the same thing as a classical gamma trading, gamma theta payoff, provided you have defined those derivatives with respect to price and time properly. And again, it is obtained by not changing anything from the past, but working on the local scenarios.
Yeah, the challenge, if I remember, Bruno, was precisely properly defining the theta, which was not so easy, and that's where you did all this.
I remember you had tried to confuse me with inductive limits and something like that. And the second question, so with local vol or Garch. So one thing is the historical estimation from data from the past, from the statistical estimation from historical data. So so you can look at the price history and try to estimate the volatility, instantaneous volatility at each point in time, and try to model the way it evolves, like again the Garch. Here it's really an implied estimation called calibration, actually. So where we don't care too much about the statistical property of the past prices, but we try to find the simple assumption on the future to be consistent with the prices that we observe today. In other words, the prices that the market is offering today contain actually a certain view of the future, and we try to reveal this view. So it's sort of addressing different concerns, but I think what is very important is to eventually merge the two, the historical estimation and the implied calibration, because it's always a big problem when you have a large discrepancy between the implied parameters that you have calibrated and the historical parameters. Just a simple example, Heston model, when you compute the volatility of volatility, you tend to find a very large number, because to generate a skew in such a model, so the skew will depend on the volatility of volatility times the correlation. And so with a big skew will force actually a big vol and much higher than what is observed historically. So I think it's very important to to make sure that your implicit calibration is reasonable.
Thank you very much, Bruno. So it was excellent talk, and as usual. And so we have, okay, we've eaten about 10 minutes in our coffee break. So we'll reconvene in 20 minutes for Carol. And I think, Bruno, you will be the chairman for Carol, if I understood well.
Yes, yes.
This second, because I was pressured by the time, so I missed wishing a happy birthday to Marco, and I owe him a lot because basically, as you mentioned, Bruno, Marco made a material change in my life by bringing me to the US. So my US life is thanks to Marco, so that I will always remember. Thank you very much. And so see you in 20 minutes, and we are switching to the chat room now.
Okay, wonderful.
See you.